All right, let's get started by taking a look at this 3 milliwatt laser pointer that's lasing at 635 nanometers. Let's input the wavelength. That's 635. Okay. You'll notice that you can select nanometers or you can select microns. Okay, and it depends on which one you want to work with. It's totally up to you, but if you've entered it one way, you select the other unit, it'll automatically change it. I'll show you the only other place the wavelength units affect is if you're looking at a single mode fiber, the mode field diameter, it will be in the wavelengths that whatever's set in the wavelength unit. So if we change this back to nanometers, you'll see that the mode field diameter is now in nanometers. All right. Just wanted to point that out quickly. So our mode of operation is continuous wave, and you have a selection here of several options of continuous wave, single pulse, repetitive pulse, and pulse groups. Of course, for this little pointer, it's continuous wave. And because it's set to continuous wave, your only options here are average power or energy. Very, very seldom, I'd say 99.99% of the time, we input for continuous wave average power. The only time, realistically, the only time I've used energy is when I'm trying to explain something. But anyway, it is available, and you can put average power here. And in this case, it's 3 milliwatts, so we can put 3 e to the minus 3. Or 0.003, and you'll see that the software switches it to scientific notation. The ANSI default exposure duration we're using is 1/4 of a second. That is the default, ANSI default, for an unintentional or accidental exposure to a visible wavelength. Now, let's say, let me just show you how that works. If we said, well, what if we had a near IR wavelength, 850, you'll see that it automatically adjusts to 10 seconds. Now, you may ask, what if I don't want this adjusting? What if I'm running multiple wavelengths in a beam? Say I'm running some visible wavelengths mixed with IR wavelengths, and I really want the exposure duration to stay at one fixed exposure duration. Well, the way to do that is just simply click this, okay? And that will stop the default from being changed when you change wavelengths if you step into a different spectral region. So let's put this back to 635, and you'll notice that it doesn't change, but if we click back on to the ANSI default, it changes back to 1/4 of a second. So we're set there. Let's put our beam parameters in, or our beam propagation parameters. The major axis diameter, we have 1 millimeter. Divergence is 1 milliradian. Now, when you're inputting these, understand that the software and the ANSI equations are really talking about the beam diameter at the beam waist. Sometimes you're going to be given the information and somebody will say, well, we know what the beam diameter is the aperture. We know what the beam diameter is at the aperture, the output aperture of the laser. For most cases, that's fine to just use that and use that as the reference and input that beam diameter. Sometimes it isn't okay. It does make a difference where that beam waist is, particularly if you're using a laser that has a beam expander. Because when you use a beam expander, we typically push the waist quite a ways out. It could be tens of meters out, 100 meters out. And so when we give the results, say for the NOHD, it's really referencing the NOHD distance from what it's assuming to be the diameter, the beam diameter at the beam waist. So if we did a calculation and we knew that that beam waist was pushed out about 20 meters, and we did a calculation that said the NOHD is 30 meters, if we wanted to tell the user, well, based from the output aperture of the laser, the NOHD is 50 meters. Okay, so just keep that in mind that for all the equations, whether it's the software or the ANSI standard, they're really talking about the beam diameter at the beam waist. So you might need to know where that beam waist location is. But as I said, for most lasers that don't use a beam expander, that beam waist is going to be pretty close to the output aperture of the laser. So we have all the information in here. Let me quickly talk about 1 over e squared and 1 over e choices. If we don't have if that criteria isn't given to us, we select 1 over e squared because it will give us a more conservative result. And most of the time, we're given parameters, the beam parameters, in 1 over e squared. And that's because laser manufacturers work in 1 over e squared. It's laser safety folks who work in 1 over e because we're interested in peak irradiance, not average irradiance. If you take the beam diameter in 1 over e and calculate the area and divide it into the power, it gives you peak irradiance. If you take the beam diameter at the 1 over e squared points, calculate the area of the beam, divide that into the power, that gives you average irradiance. In safety, we're always working with 1 over e. So even though you've input 1 over e squared, the software changes to 1 over e, and I'll show you in just a second sort of how that works. Okay. So we have all our parameters in. The only one we haven't talked about is m squared. With the diameter divergence, m squared can be calculated. Now, what we really like m squared for is when we're given the diameter and an m squared value. If we input the m squared and the diameter at the beam waist, then the minimum, the lowest divergence, will be calculated by the software for the m squared value you put in. So sometimes the manufacturer will give you the diameter and the m squared value, put that in, and the software will calculate the minimum divergence for that m squared and that beam diameter. We also have observer range. This is where we set where we think our observer may be, or of whatever we're interested in at the distance away from the beam waist, or the reference point, the beam reference point. If it's the aperture, then it's, if we're calling it the aperture, then it's the how far away the observer is from the aperture. Okay. Now, we don't typically do anything closer than 10 centimeters because if we're looking at a point, your eye can't focus any closer. If you move any closer, your eye can't focus any closer than 10 centimeters, and that's really for a young eye. So we default at 10 centimeters, but a more realistic value for this, a minimum realistic value, would be a half a meter, and that's what we're going to use here, is a half a meter. And you can see that the beam diameter changed a bit to 1.118 millimeters because what happens is the system calculates what is the beam diameter now at this observer range, because that's what we're interested in. We want to know what's happening at the observer. You'll notice that the OD at observer range is 0.486. Also, the worst case is 0.486. The worst case OD says no matter what size the beam is, we will assume that all the power is passing through the limiting aperture. Okay, so here's your limiting aperture, and remember that when we do calculations in laser safety and we're calculating the irradiance of the laser, we pass the power through the limiting aperture, and then we take that power and we average it over the limiting aperture. So we'll talk about that a little bit more in just a moment. So let me kind of give you a demonstration of that. Let's put the observer out at 10 meters. Okay, you'll see the beam diameter has grown to 10 millimeters. So the OD has dropped to 0.28 roughly. What that's saying is that for this beam diameter, you can't get all the power through the 7 millimeter aperture, even though for worst case, we're still assuming that's the case. You're getting all the power through it. All right. So how much power at 10 meters are we pushing through the limiting aperture? Well, you can get that right here. It's 62% of the power is passing through the limiting aperture, and if I click right there, I can see that the power passing through the limiting aperture is 1.86 milliwatts per square centimeter. So if I take that power and I divide it by the area of this limiting aperture, let me click that. The area of the limiting aperture is 0.385. So if I take 1.86 milliwatts, I divide it by 0.385 square centimeters, then my average power irradiance of my beam is 4.84 milliwatts per square centimeter, and you can see that's a little bit higher than in my MPE. We'll come back to the MPE in just a second. So I do have an OD value. Let's put the observer range back at a half a meter, and you can see because of the size of the beam, we are now getting 100% of the power passing through the limiting aperture, which is 3 milliwatts. Okay, so again, let's take a look at the average power irradiance. That is 3 milliwatts here. or you can get it here, the 3 milliwatts divided by the area of the limiting aperture, and that will give you 7.8 milliwatts per square centimeter, and then that is compared to the MPE to get this OD range. Realistically, how it does it, it takes this irradiance, divides it by this MPE, and it takes the common log of it, and that's how you get the OD value. Okay? So I think you've already figured out the MPE is reported here. Here is the MPE for the skin. You'll notice it's a lot less restrictive. It's 3.11 watts per square centimeter. Now we don't have anything like OD value to give you an idea of the hazard to the skin. So what we do is we give you the ratio of the irradiance of the laser based on the skin limiting aperture, how much power is passing through that, and then that's divided by the skin MPE, and that ratio is what we report here. So if this ratio is 1 or below, you do not have a skin hazard. If it's above 1, you have some type of skin issue. Okay, and we can see from this that it is 0.01, so there's no skin hazard at all from this laser. All right. Okay, so we've taken care of most everything we just kind of wanted to hit on quickly. One thing I did want to do is come back up here to the 1 over e squared, 1 over e. I said that if you select 1 over e squared, it gives you a little more conservative result. And that's because what the software does, it takes the 1 over e diameter at range, divides it by the square root of 2 to get this diameter in 1 over e. So that diameter becomes smaller, as does the divergence. The divergence, we take 1 divided by the square root of 2. So what the software is working with is a beam diameter at the beam waist of 0.707 millimeters and a divergence of 0.707 milliradians. So that's what's happening right here. Takes the 1 over e squared, converts it to 1 over e, and works with that. But if I say these are my 1 over e, well then I would expect my NOHD to get shorter, not as long of a distance. Let's change it and see, because there's not going to be any conversion, right? It's going to use the 1 milliradian beam divergence. And sure enough, our NOHD goes down. Okay, so that's why we say if you're not sure, use 1 over e squared and you'll get a more conservative result. I could do the same thing here, but if I just say, well, this is an elliptical top hat, you'll notice that the NOHD drops a little bit because it being a top hat beam, and we don't have that picoradiance in the center as compared to a little further out on the edges of the beam. Okay. That's really a discussion for later on about how that works, but I just thought I'd show you that. Gaussian always gives you a more conservative result along with 1 over e squared. Now before we leave this, since how we've got a few things going here, for visible wavelengths, we know that for class 2, the exposure duration we use for looking at classification and determining if a laser is class 2, we use 1/4 of a second. That's our class 2 exposure duration. But really when we're classifying lasers, we're talking about the AEL. Okay, so the accessible emission limit. And we've already learned that the AEL for class 2, the limit is 1 milliwatt. Okay, so what we'd like to know is, well, where do we find that? Because the way we get the AEL is we take the MPE, which is in watts per square centimeter, we multiply it by the area of the limiting aperture, and we wind up with the power that would be associated with this MPE. Or we can just click here, and that gives us the AEL for whatever exposure duration we're looking at. Now, I know that we said the limit is 1 milliwatt. Mathematically, it's 0.98, but we round to 1 milliwatt. Okay, so we can test that. Let's put 0.098 in, and we'll see that I guess I put a little more than that, 0.00098. That should do it. That's 0.98 milliwatts. Okay. And we can see that our OD at observer range is 0. Of course, our worst case OD is the same. Now, don't be alarmed that that we actually have a bit of an NOHD here, because this is a mathematical thing about the divergence and numbers. So this is just saying that we have a little bit of, we're not quite at 0 yet. Okay. So don't worry about this. This is common. This has to do with just math. Let me put 1 milliwatt in here. And you'll notice that we have just a little bit of an OD value here. Okay, so that's really what's going on. You'll notice that the NOHD went up a little bit. Let's put 0.097 in, and you'll notice that, again, I did it again, 0.00097. Okay, and you'll notice that, yeah, now we go to 0. So it's just about how numbers are getting rounded off and things. So don't be alarmed if you see that for a particular, the OD goes to 0, but you still have a little bit of an NOHD. It's just a number of things. Now, you'll notice that when we don't have an OD at the observer range, we report the fraction of MPE, just to let you know how close to the MPE you are. So if we run up just a little bit, 0.123975, yeah, we're getting a little closer to this. So it really is 0.00098, and that takes us, that's actually a little bit, we have just a little bit of an OD at observer range, but it's gotten rounded to 0, where if we, of course, go to the 1 milliwatt, we then are able to detect that little bit of OD there. I really think that's about all I want to talk about here. That's it.